Hey everybody, welcome back to Organic Chemistry. Now we're going to do Chapter 13, Part 2C. So the last thing we need to do, these are the last topics for this chapter. And so let me just tell you what they are. The Diels Alder reaction, determine the reactants, that's what we're going to do right now. Following that, we're going to do orbital description and explain endo, exo, and how that all applies to this whole idea. Following that Diels Alder reaction, we're going to do the intramolecular Diels Alder reaction, and that has some interesting ideas to it. And then the final thing is talking about something known as symmetry allowed versus symmetry forbidden. And it'll help us to determine when reactions can or cannot take place. So that covers it. This is going to be the last stretch. It'll be one video to cover all these different pieces, and then we'll do the final problems to wrap up. Okay, so let's get started. Let's talk about the determining of the reactants. Now, what I did here is I wrote out this because I hate writing these rules out. And to be honest with you, you're never going to use these rules. But it's just that people like rules, right? So this is something that you can work with if you want to read something and kind of work through it. This is the rules. But what we're going to find is that the process of determining the reactants from a product is not so much about rules that you have to memorize like this. It's by practice, okay? So we're going to do a few problems together, and I assure you by the time we're done with these problems and then the homework problems that we're going to do together, that you're going to be fine. You're not going to have to write these rules down, okay? But I did take the time to type it because every year I write it and it's really annoying. Anyway, so here are the rules, and I already see a typo. Sorry about that. Determine. Anyway, so you're going to find the six-membered ring. Now that's very important because Diels Alder reactions make six-membered rings. Once you do that, you're going to figure out where the double bond is, and you're going to label it as C2 and C3. Now, sometimes there might not be a double bond, and we'll see that actually through the problem, the homework I'm going to give you, and then we'll do together. But so most of the time it's there, but they could try to trick you, and I'll explain how that works later on. But you look for your C2, C3 double bond. Once you label C2 and C3, then you could work around for number 1, 4, 5, 6, right? Because you know C2, C3. After you do that, you break between C1 and C6 and C4 and C5. And then you're going to make a double bond between C1 and 2 and then C3 and 4. And we'll see this in practice in a moment. Add a pi bond. See, I wrote pi bond. I didn't write double bond because it might be already a double bond on 5 and 6, which in case it's a triple bond to begin. Okay? And again, you'll see all this in practice. Determine if C5, 6 are cis or trans, and then determine if it's a C or T position for C1 and C4. This is the way you work backwards, okay? And like I said, you're not going to write this down. It's here for you, but you're never going to write it down after this. Let's just practice. So I'm going to give you 4 examples, and each one will build upon a little bit more complexity, but by the time we're done, you'll get it down, and you'll be very comfortable with this. Okay, so here's how it works. So we're looking at this product, and we know that this is, with heat, some sort of DA reactant, right? So we're looking for a diene or dienophile. Well, the first thing is you have to find your six-membered ring. Here it is. And what we're going to do is we're going to see that there's a double bond, and we're going to call it number 2 and number 3. Now, is it 2 up, 3 down, 3 down, 3 up, 2 down? Doesn't matter. Just number it however you wish, okay? So here's 2 and 3. And now that I have 2, 3, I know that this must be 1, this must be 4, 5, and 6, okay? So now what I'm going to do is I'm going to break between 1 and 6 and 4 and 5. And I'm going to separate them out. Now, what I'm going to do is for the diene side, I'm going to draw it like this. And for the 5, 6 side, so here's 1, 2, 3, and 4. Here's 5 and 6. Now, for 5 and 6, let's handle that right away. We're going to put a double bond between them, a pi bond. And since there's a single bond at the end, it must be a double to begin. And then we're going to look and see, okay, this is back and this is wedged, the methyl. So that means that it's trans, right? So we have we have over here double bond O, and then that must be trans. Now it doesn't matter if it's left or right for the double bond O carbon, and because it's just flipping it, right, like a pancake. So don't worry about which way, left or right. And that's your answer. This is the answer for the dienophile. Now let's work on the diene. So for the diene, we have to put a double bond instead of between 2 and 3. That's what happens at the end. So to begin, it must have been 1, 2, 3, 4, right? And then if we have something on the wedge, remember this little chart here where we know that if it's the T position or the C position, well, once you make the ring, the T is going to be in the back and the C's on the wedge, right? C's on the wedge, T's in the back. So since the methyl's on the wedge, it must be pointing in C position on number 1. Since 4 has a methyl in the back, it must be pointing in the T position. And these are my 2 starting materials. You see that? That's it. So what I did is I followed all these rules here to get to the end, okay? But like as you could see now, you don't really have to write the rules down. All right, let's do it again. Let's try another one. Again, we're going to do 4 together, and then you're going to do some homework after we're done with this whole video set. All right, this is a little bit more complicated, right? Because now, where's the 2-3 double bond? Well, we have 2 6-membered rings, so the reality is that we could say this is 2-3, this could be 2-3, or that could be 2-3, right? Now, I'll tell you right now, the one that's not going to be 2-3 is the one that's next to a carbonyl, right? Since this right here is an electron withdrawing group, C double bond O, you don't want the diene, the 2-3 side, to ever be near that, okay? Because that's your indicator that that should be the dienophile side, not the diene side. So we know this is out for sure, these 2. So now we're left with the left or right or the middle 2-3. And the truth of the matter is it could be either of those 2. You can have the answer either way. However, we would find a problem because if we called this, let me show you. If this is 2-3 all in the left, this is 1 and 4, this would be 5 and 6. Now here's the problem with 5, 6. It's going to be very hard to make a triple bond in a 6-membered ring. You see that? So if we broke here and here, the problem is you have to make a triple bond in that 5-6 position. And you're not going to be able to do that in a stable way in a 6-membered ring. It's not very happy. So that's why that doesn't seem to make sense. So I'm going to rule that out. So now we've realized that, okay, we're done with this is out. This doesn't make sense, or that one to be 2-3 for the reasons I just showed you. So now we're going to be set for what I have here in the middle. If that's 2 and 3, or you could have flipped it the other way around, this is 1 and 4, and here's 5 and 6. So let's break between 1 and 6, 4 and 5. Okay, so let's do the left side first. We have this system like this, right there. And then we have our 1, 2, 3, 4, right? And we'll come right back to that. Here's my 5 and 6. And notice that 5 and 6 have a double bond at the end. So if we add a pi bond to it, it becomes a triple bond to begin, right? It already was a double at the end, and you always remove one, so you have to add back in that pi bond. And then on 6, it has a carbonyl attached to it, right? So let's put it back in. Remember, triple bond is just a straight line. That's all it is. It's a linear structure. So you don't have to bend it or cis or trans or anything like that. And that's it. Now we've taken care of our dienophile. We've got a triple bond to begin. Now let's deal with the diene, right? So 1, 2 should be double bond, and 3, 4 should be double bond. And now since 1 has a methyl in the back, that means it's in the T position, and 4 has a methyl in the back, so it's in the T position. And that's it. These are my 2 answers. You see how we did that? And you see how we worked the logic? We thought maybe 2, 3 could be here, and then we realized, wait, we don't want to put a triple bond in a 6-membered ring, and so that's why we worked the other 2, 3 position. All right, so this is a little bit harder, but I think after the 4, like I said, it's going to make a lot of sense. Here's another hard one, right? Not really, just looks complicated. And so all I would say that you do is just take your time and think about this for a moment. First off, there's a lot of things going on here, but all we care about is the 6-membered ring. That's my point of reference. And there's only one double bond position. So this must be 2 and 3, right? Okay, so if that's, now you might say, well, look, what about this whole carbonyl on the side of 1? Well, you know what? It's really not a carbonyl on the carbon 1. It's an oxygen that's on carbon 1, and that has a lone pair. So this